Hello, my name is Mustapha Ishak, and I am a professor at the University of Texas at Dallas. I will talk to you today about testing gravity at cosmological scales, or testing general relativity in cosmology. Here is a picture of my students in summer 2018. I will name some of them during the work that I will describe in this talk. And then also these projects have been funded over the years with NASA, NSF, or DOE. I will start my talk by saying the word impressive for general relativity, a theory that revolutionized our understanding of space and time. It did give us a theory of gravity that is more accurate than Newtonian theory. It did give us a Big Bang cosmology of an expanding universe that has encountered so many successes. It predicted the existence of black holes and gravitational waves. It also makes our GPS work today, and otherwise we will be 10 kilometers off per day. In fact, it is quite remarkable that the equation of Einstein, since he proposed them in 1915 up to now, more than a century, are still in the same form as proposed. The cosmological model received so many successful discoveries and progress and so forth. However, this didn't come without any puzzles and surprises. So first of all, there is the problem of dark matter. And so it happened that 90% of the matter in the universe is in some form that only interact via gravity. And then there is the problem of cosmic acceleration in the dark energy. So the universe is expanding and is speeding up in that expansion. It's not slowing down. And these observations have been there since 1998, so for 22 years ongoing. And so we do not know what is the reason why the universe is speeding up in its expansion. And third, there is this problem of cosmological discordances. So we enjoyed the glorious years of concordance cosmology, but now we started seeing some discordances, persistent inconsistencies. Well, the question that comes to mind, are these problems related? Or maybe just two of them are related and maybe all of them are related. So what comes to mind is the underlying theory. Do we have the right theory in hands? And in fact, testing general relativity at cosmological scales have several motivations. The dark sector and cosmic acceleration, as we just said, but then also the cosmological discordances. And from the very beginning, there are some intrinsic open questions about GR, its singularities, and so forth. So there is a quest also for unified theories of physics. And also the simple fact that now we have the data, we have the technology that we can test cosmology at, we can test general relativity at cosmological scales. How we do that? How do we test gravity at cosmological scales? There are at least three methods that have been developed. The first one is phenomenological parameterization of the field equation. So we put some parameters that represent deviations from GR. This is very popular. In fact, it is a smart approach in a sense that even if we do not know the modified gravity model, we will first, as a first step, try to just see whether GR is consistent or not. Then the second method here is testing specific models of modified gravity model theories. And The third one is pursuing these observed inconsistencies and try to dig further into them if they are the symptom of some problems with the theory. And the way I will present my talk here is that I will give 1 or 2 slides about the background, and then I will tell you about the work that I did with my collaborators and with my students. So you can find more background in this review, this 204 pages review in Living Reviews in Relativity. I wrote it with the graduate students in mind and people who want to join the field. So you can find it either on Living Reviews or on AstroPH. Now I will talk about the first approach here, the phenomenological parametrization of deviations from general relativity. Well, modified gravity models, they can give us the same history of cosmic expansion as WCDM or as lambda CDM. So they will be undistinguishable as far as the expansion history is concerned. However, now we have large-scale structure formation can actually help us to break this degeneracy. In fact, it's a blessing because we have not only the expansion history, but we have structure formation history. And the two need to be consistent with each other. They complete each other. And in fact, in this case, large-scale structure constraints, they break the degeneracies that in the expansion history. The framework to work on that is the Perturb-Einstein equation, is perturbation theory. So we consider the perturbed metric, Friedman metric, and then we use the Einstein field equations to obtain the perturbed Einstein field equations. And they give us these equations here. The first equation is a relationship between the potential psi and the sources of the space-time, the matter density and so forth. And then they are related by this, but then we insert also a parameter mu for modified gravity. In the case of GR, this mu is equal to 1, but in modified gravity, it deviates from 1. This is for the motion of the matter or massive particles. Next, we have an equation that represents the difference between the two gravitational potentials. In GR, eta is equal to 1. So late times where there is no shear in large-scale structure, so we have that psi is equal to phi in GR. However, in modified gravity, even if there is no shear, so you can still have that eta or gamma, they represent the difference between psi and phi. We call this the slip parameter, eta or gamma. Next, we can combine the two equations and combine them in a third equation and obtain what we call the Weyl potential up to a numerical factor. So this Weyl potential is related to the sources of the space-time, the matter content and the momentum and so forth. So these are related also. There is also a parameter sigma that comes here, which is a combination of the two other parameters. So this equation is also very important in cosmology because it represents the motion of light, the motion of massless particles. So we're talking about the motion of photons and so forth. So we're talking about gravitational lensing. Well, again, in GR, we need only two of these parameters, two of these equations, and to do the work. And because they are related, the third one is related to them. So in GR, they are equal to 1. However, if we measure a significant departure of these parameters from 1, that will be indicative of some troubles. There are parameterized forms. There are some functional forms for the parameter mu and sigma, and either just a function of redshift or the function of redshift and scale. So if you look, these forms have been motivated or kind of constructed depending on late time behavior or early time behavior, either in the redshift or large scale behavior, smaller scale. So there are some asymptotic or limiting points as guidance to do this. So Planck, DES, and CFHT lens and so forth, they use these forms and they became popular. They are used. The question that comes to mind, are these forms bringing some limitations? Some papers argue that yes, and in fact, including one of our papers. So are there alternatives? Yes, there are the binned forms. We can use without specifying an ansatz. We can just use bins, low redshift, high redshift, 2 bins in redshift, in fact, even a third one. And then we have bins in scale, large scale, small scales, and then we can make the cuts and so forth. These are surprisingly less used in the literature, and I suspect maybe the reason is that the codes that do MG models or MG parameterization, most of the codes don't have this binned method implemented. And again, as I said, so these parameters are propagated into power spectra, correlation function, observable functions, so we can constrain them using the data. And that's exactly what I did with my student Christian Garcia, and also students Fox and Dossett, and also with Christian. So we wrote a series of papers, and we used all the data that is available, Planck data, baryon acoustic oscillations from 2DF, from 6DF, from SDSS, BOSS, you name it. All the BBN and HST, DES data, Planck 18 and so forth. So over the years, for the last 5 years, we do have a paper that is like about 3 years or 3 years before this or 4 years before this. We find a consistent tension when we use the CMB data, and then we reinforce it, like in these 2 plots here, this plot and this plot here. We find a consistent tension with GR when we use CMB and BAO, RSD, and BSH. But the main driver is actually a Planck. So if you look at this line here, dashed line, and this dashed line, these are the GR. So this is the point predicted by GR, and this is also point predicted by GR. So just by eye, you can see that there is a tension. In fact, there has been a tension over the years, even with Planck 2018. So we see that if we don't use lensing, there is a tension of about 3 sigma or more. But when we add lensing, CMB lensing, we see that the tension goes away. And this has continued, this pattern has continued, that we do have an over 3 sigma between CMB and 3 sigma tension with GR when we use the CMB. When we add to the mix lensing, CMB lensing, and DES lensing, that restores the consistency. You see it here as well. So the point here, you see the blue and the gray are far from the GR point. When we add them in green here, we add the lensing data, it restores it. Same here. You see the gray and the blue are inconsistent with GR point. So when we add lensing, the green here becomes consistent with GR. We said, what could we do next? What we decided to do next is to single out parameters, modified gravity parameters. Why? Because we wanted to obtain more power from the data sets, but also we wanted to dissect this tension, see what's going on farther with them. So I very much like these 4 plots, because let's look at this guy, and this guy, these 3 plots. So you see that when we used in blue here the CMB constraint, Planck 18, we add to it supernovae, BAO, or we add to it also RSD, and we add to it all of them BAO, supernova, RSD. You see here and here and here. They are far away from the line of GR. Here we fixed mu, we fixed eta, and here we fixed mu. And then here below we fixed mu and we let sigma vary. So you see that a pattern is coming. So first of all, the tension of these guys and this are about 3.9 sigma now. And then if we add CMB lensing, green and gray, if we add CMB lensing, it goes below 2. It goes actually, it becomes like not significant at all. And in fact, if we add the DES data in red and purple, you see that it comes to touch the GR line here. So we have consistency then with GR restored by lensing. So again, the question, why are we having this dichotomy between Planck and lensing for GR? So maybe some answer comes from this fourth plot, because when we look at sigma here, we fix sigma equal to 1, and then we fix sigma equal to 1, so we see that all over the board we get consistency with GR. So it could be that Planck is not constraining well sigma, in fact doing things that it shouldn't be doing, and giving us this inconsistency with GR. Can we do more? Yes, we can do Bayesian model selection analysis, or Bayesian model analysis. So we did do the Bayesian analysis here, and to compare whether modified gravity are preferred or lambda CDM are preferred. Usually lambda CDM is always preferred, because we vary the two parameters, mu and eta, mu and sigma. And you can see that in these two lines here, we do find consistency, and we do find also that GR I correct. So even if we find an inconsistency with GR, but yet lambda CDM is preferred, okay? However, that is not the case now. If we modify only one parameter, if we vary only one parameter, if we vary only eta or sigma, so not only we get about 3.9 sigma in consistency with GR, but we also find that such a model, such an MG model, is actually moderately preferred by the data. So this is an interesting result, and so we again find that the last line here is when we fixed sigma equal to 1, and in that case then lambda CDM, not only there is no tension, but lambda CDM also becomes the favor model. So again, we do find a persistent tension. And again here, if we add DES data of CMBL, you see in all these columns here, you see that lambda CDM becomes again the preferred model. So it was a good idea to single out these parameters. And so we see that not only the significance of the tension increases, but also the Bayesian analysis gives some preference to modified gravity model with one parameter. Well, we looked into the scale dependence now, even if we have relatively not enough constraining data, but with the trick of varying only one parameter, we find when we fix sigma equal to 1, the parameter, we find no inconsistency with GR all over the board. However, if we fix mu and we let sigma vary, so we see that again towards smaller scales we find, and when we don't use lensing, we find an inconsistency with GR at the level again of 3.5 sigma when we go towards smaller scales. And then if we put at CMB lensing and DS lensing, the tension goes away. So the pattern is clear, no matter the parameterization we are using, and there is some dichotomy between Planck and data lensing data. We pushed it even a little bit farther. We said we will actually use the binning method. We do not have enough data to do the constraint in both scale and redshift and the binning, but we gave it a shot and see what we get. And what we got is a consistent picture. We did get again, so here we vary both mu and eta, and we find that in low K consistency with GR, high K going a little bit towards smaller scales, we get some inconsistency with GR. And then we said we pushed it even a little bit farther. We said, okay, we fix one parameter and we vary the other parameter. So we fixed the mu's and we varied just the sigmas. And when we vary the sigmas, so again, we find some inconsistency at high K. So the inconsistencies here are of the order of 2.2 and 2.4 sigma. So because of the large number of parameters, we get the ellipses get a little bit larger, but yet there is some mild tension there. So, and again, with the model, sigma is marginally preferred over lambda CDM. So this is a pattern that is continuing. We see it all over the board here and different binning or functional parameterization. So this we have to watch this with the incoming more constraining data. If you're curious why what we used to do the work, we used ICTP-SAIFR, the integrated software in testing general relativity. With my students at UT Dallas for the last 5 years, we developed this software. It does the things that other software do, and dynamical dark energy, massive neutrinos, and all the parameterizations. It does a few things additional that other software to our knowledge don't do, like the binning method and the curved or flat. So the curved, we do also curved background. Good. So now the last thing I would say about this approach number one, or the first approach, is that we can also use the growth index parameter. And so we have the growth rate function f, and this growth rate function f, we also have an ansatz that represent this growth function as omega m to the power of gamma. This gamma is the index parameters, the growth index parameters. Well, interesting, this gamma is a good discriminator between theories of gravity. And it can be constrained by redshift space distortions and few other types of observations, like Dizzy is very strong on this. So gamma is equal to 0.545 for lambda CDM, 0.687 for modified gravity. In fact, the interesting thing is that they can have some scatter, like if you change W, blah, blah, and so forth. So you will get some scatter here. If you change the parameter for DGB, some scatter, but they don't touch, they're still far enough one from the other, so gamma works. I did some work some time ago with some collaborators here and students as well. Good. So testing specific modified gravity. This is approach number two. The approach number two. So as I said earlier, there is a number of modified gravity models in the field, motivated by various reasons: f of r, f of g, DGP model, bigravity, no local gravity, Horava-Lifshitz theory, and so forth. Interesting set of models. And actually, however, it's difficult. It is difficult to constrain them and costly, because we need to develop not only the observable to do it, but we need also to produce simulations for the nonlinear regime. And that's, however, good progress is being made, for example, using the COLA simulations. And also, there are also certainly some brave analysis for f of r models, no local gravity, and some started some shy analysis about the Hordensky and beyond Hordensky models. So it's worth keeping an eye on that. I will talk a little bit about some of the work I did with my collaborators in this approach too. So there is based on the COLA simulations, we developed for the LSST dark energy science collaboration, we developed an emulator for the matter power spectrum for F of R modified gravity cosmologies. It is fast. It is fast. It can do an evaluation for prediction of F of R matter power spectrum in less than a millisecond per computation, and it does it on an Intel Core i5 processor. So this is 10 to the 6th time faster than COLA approach. And we already said that the COLA approach is actually much faster than the N-body simulation. There is ongoing effort to put this emulator into the core cosmology library of LSST disk. Well, I will just briefly mention in the past, so we did some work on FG model. The Gauss-Bonnet have some nice theoretical motivation. We, with my student Moldenhauer, we compared it to observations and so forth. It did well, but actually it's the instability in structure formation that was the showstopper for at that time. But I do see that there is some renewal of other stable variants of this theory. See, for example, a paper by Clifton et al. 2020. Yeah, so approach 3 now. The third approach is to look farther into these inconsistencies. So we said that if there is some inconsistencies between data sets, the full volume of the data sets, if there is inconsistency, it could be due to systematic effects in the data. It could also be due to problems with the underlying gravity theory. And so it's worth digging farther into it. It's worth developing tools to dig farther into it. And my group and other people in the field are developing some new tools, new measures, and new metrics, and so forth. I would like to mention one thing in this consistency tests is something, a work that I did 15 years ago about the consistency with collaborators, with my collaborators. So I thought at the time I was thinking about how to go beyond the W. I wrote a good paper on W, and with collaborators. We spent a really good time on doing constraint forecast and things like that on W. And then I thought, how can we go in another paper, this paper, how can we go beyond W? And the idea is to look to consistency test between the growth rate of large scale structure and the expansion history. So in using some mock data, some simulated data, we showed that if we assume the wrong model of gravity, if like we try to use a WCDM on a modified gravity, that's going to lead to inconsistencies between dark energy parameters. Much later, most recently with my student Lynn, we continued to try to develop these mathematical measures or metrics to characterize inconsistencies. And there is various criteria like deviation between the likelihood maxima, the volume of the covariance, the degeneracy direction, and so forth. So this is in order to dig further in these inconsistencies and try to see, even to dream whether we can kind of have some measures that we can kind of correlate with systematics and see whether we can determine whether the inconsistencies are due to systematics or rather to physics, to gravity physics, and so forth. So with my student Lin, Wei-Kong Lin, we developed this called the Index of Inconsistency. It's based on statistical and mathematical theory, but also on some heuristic thinking. You can get to it in two different ways, and we showed that in our paper. So we started with this kind of delta chi-squared, that is the sum of two delta chi-squareds, and this is each of them, like for two experiments. So we have this delta chi-squared. Each of them is the chi-squared based on the joint analysis minus the chi-squared based on the individual analysis of the experiment. So in other words, and then we sum them up for the two experiments. So in other words, this guy here, this guy represents the difficulty for the first experiment to support the mean of the joint analysis, while the second one represents the difficulty of the second experiment to support the mean joint analysis of the two experiments. And then we sum them up. And we use the Jeffrey scale to look into how to characterize the inconsistency. And in fact, in one dimension, there is a very simple relation with the n sigma notation. In fact, when we go to the Gaussian limit, we get even a more specific form of this IOI. And in fact, we can also generalize it to multiple experiments, not just two experiments. What I like about the IOI is that it looks into the whole parameter space of not just singling out one parameter at a time, but it gives you an overall inconsistency between two data sets or multiple data sets. We used all the data available each time we do the analysis, you name it. So local measurements, CMB, large scale structure, and we applied this to the different comparing different data sets, contrasting and look for inconsistencies. So first of all, we calculated the H naught from each of the these probes: Planck, shoes, joint large scale structure, holy cow, supernova BAO plus BBN, and other data sets. And then we actually cross-checked each of them and checked for inconsistencies. So not only we recovered 9.7 IOI for the Planck versus shoes, with no surprise that the largest one. Since this is one parameter, to find the sigma, you see is greater than 5, IOI greater than 5. That's very strong inconsistency. To find how many sigma it is, you take this 9.70, you multiply by 2, you take the square root. So it's certainly for sure above 4 sigma at the time. Now it has gone a little bit up. And we did find something also. We did find that shoes, the local experiment, is in tension with joint large scale structure with 6. So if you multiply 7 by 2, that's 14, and you take the square root. So it is also a strong inconsistency here. We did apply the next to the large scale data. And again, we should remember that we're comparing all the volume of the cosmological parameters as determined from the large scale structure, and also the one determined from Planck, and then the temperature, low E modes, TE, low E, and so forth. So we do find that when we combine large scale structure and we compare it to CMB, we do find an inconsistency of 5. Again, it's not low, it's moderate to strong inconsistency. So this is consistent with other works that looked into just the Planck versus large-scale structure, but based on sigma 8. But we don't use just sigma 8, we use the whole parameter volume space. And so it is consistent. So now the question, this H naught problem, this mg tensions that we found, and this tension that is continuing also for sigma 8 This is an old thing, sigma 8. It goes back also to a number of years, and it's there, it persists. So now, is this a sign? These sign of departures from GR or problem with the models, or all of them are the sign of systematics? We are very much hoping that with LSST, DESI, WFIRS, GWST, and Euclid, Simon, and so forth, we will be able to know more about these. So very good questions have come up when we look at testing general relativity at cosmological scales. So some concluding remarks and some questions. So of course, so there is testing general relativity at cosmological scales, have several motivations, with cosmic acceleration certainly at the front of them. We also have at least 3 approaches to test gravity at cosmological scales: parameterized deviations, testing specific models, as we said, and pursuing these cosmological inconsistencies. When we look at parameterizations or deviations from GR, we can also use the binning methods. The binning methods, we don't have to impose a functional form, and this may help us to circumvent some limitations of some functional forms that were discussed in some of the literature. One more thing, the current data sets, they do show a persistent tension above 3 sigma using Planck, and using Planck plus supernova plus BAO plus RST. So this has been there, is continuing for some years now. If we add lensing data, the tension goes away. And so we talked a little bit what could be the reason for that. Now, so why such a dichotomy between Planck and lensing for MG? We don't know. And we discussed it in a paper, possibly that the solution, possibly not. There is also, we have to keep an eye on the emulators when testing modified gravity models like Hordensky and beyond. And these may make the difference in the future in approaching these models and testing them. And again, a question is open whether these tensions are an early symptoms of problems with gravity, or they are simply due to the data systematics. There is a lot of data coming, a lot of promising surveys are actually running in this time and getting data, and some like LSST to start very soon. So we will have a lot of data to do some conclusive test and to get some decisive answers. Okay, so it is exciting times. We do have the questions, we have the data coming. So it is a good position to be very optimistic. Thank you for your attention, and I will stop here.